Merci. Okay. So when I had scheduled these lectures, I thought, of course, that lecture 5 I was going to be telling you about inertial effects in flying collectives, which I will not tell you about, but you could take a look on my website and see a paper or two there. So I'm going to finish up the material on models, continuum models of the hydrodynamics of groups of swimmers based on this kind of simple rod-like microscopic theory that we developed. And I'll talk about their instabilities, and then I want to try to do all this in about a half an hour, because then I thought I would just tell you about something different. So there were many choices that I mentioned. I chose one, which is what always happens. And so I'm going to tell you about some problems in cell mechanics, okay? Which has some fluid mechanics as part of it, but not the central part, actually. So where we were last time is I had written down a kind of Fokker-Planck equation coupled to a simple momentum balanced Stokes equation that was being forced by an active stress. And it looked like this. So I have a distribution function, and it satisfies, I'll write it in a particular form that I find useful. So this was just the deterministic conformational flux for a swimmer in a non-dimensional form. It says I just move along my orientation direction p. So this psi, it's a function of position of swimmers, orientations of swimmers, and time. And so mod p is equal to 1. So this is a 3 by 2, or rather 3 plus 2 plus 1 dimensional theory. 3 positions in space, 3 coordinates in space, 1 orientation on the unit sphere, and then time. So simulating this is not cheap. And so there are methods in which you remove degrees of freedom in P called moment closure schemes. I won't say too much about that, but you can, again, take a look at some of the review articles and you'll find information on that. Okay. And this was Jeffrey's equation. Ooh, I forgot a psi. So this was Jeffrey. And then I had, since I've already taken up P, I go to Q, a momentum balance equation, which really comes out of Bachelor's formula. So this P and U are some coarse-grained variables. And this is minus alpha div dot D. And D, I'll remind you, is the second moment, the tensor of second moments of the psi distribution with respect to P. Okay? So that's the whole thing. And so I was going through a list of properties of this equation. One, psi identically a constant, which in the way this problem has been scaled, I will tell you is 1 over 4 pi, is a state of uniform isotropy, and that is a steady state under consistent boundary conditions, say periodic or open, is a steady state for this system. I defined an object which I called E, which was the conformational entropy. Oh, I called it S. Good. It's E in my notes because I couldn't figure out how to do a script S in this stupid software package I use. And so this is integral over space, integral over the unit sphere, psi over psi naught, log psi over psi naught. And this had the property that it's non-negative and equal to 0 if and only if psi is identically psi naught, the isotropic state. So the isotropic state is the minimum of this energy-like quantity. Okay? And then I gave you, and this was then a homework assignment, which perhaps some of you have gone through, to calculate the derivative of this thing. And it turned out to be 4 pi s dot is minus 6 upon alpha. And I'll remind you that in this was the activity parameter, which in the way I scaled it is a purely geometric parameter. It's signed, but other than that, it's purely geometric, and it has to do with the way that drag and propulsion are laid out on a body. So here, alpha greater than 0, those were pullers. Alpha less than 0, these were pushers. Okay. And so this was minus 6 over alpha dvx, and then it's the contraction of the symmetric rate of strain against itself. So this is the object that usually you would call the rate of viscous dissipation for the Stokes equation. And then minus a definite term, a negative definite term, which was d mod grad x log psi squared plus little d mod grad p log psi squared. Okay, so then the lesson that came out of this is that if I have pullers, then S just decays down to 0. Okay, to a state of isotropy. So I'll just remind you, though, this is a really stripped down theory. It does not account for particle-particle interactions directly, except through a mean field, which is being produced by stresses and producing a flow. So there's not any information in there, though you can generalize things, that have to do with collisions or excluded volume interactions or alignment interactions, these kinds of things. So it's a dilute to semi-dilute theory. Pushers, then activity, can drive up S, i.e. create fluctuations. And in that sense, compete with dissipation. There might be some sort of balance with dissipative mechanisms. Okay, so that in the simple theory is your first clue, though I've given you many heretofore, of the strong difference between pusher and puller types of stresses. Okay? Now, I'm trying not to make asides today because I want to go a little more quickly, and asides take time. But if you take a look at Doyle and Edwards, and they're talking about the dynamics of rigid rod suspensions, essentially a theory just like this, except there's no self-propulsive part here. So in the classical Doyle-Ansauger theory, there would be no propulsive part here. You would just have this velocity. And it turns out that there's an extra stress that comes from thermal fluctuations, rotational fluctuations on these rods creates a stress. And that stress is a de-stress again, and it's a dissipative sign. Okay, so In the case of pullers, it looks exactly like Doyon-Sauger theory for a dissipative system, except for there's this extra P part. This is propulsive part. And of course, this activity stress for pullers is not thermodynamic. Okay. Now, I want to make another comment about this. This identity and any of the stability results following does not depend in its qualitative result, instability, stability, these kinds of things, does not depend on swimming. It depends on the sign and presence of the active stress. Yes, the self-induced motion. It really just depends on the flows that are being produced around the particle, these dipolar flows. So a useful exercise, if you're doing this calculation of the entropy, is just to stick the swimming speed back in there as a placeholder, and then to work through the whole thing. Well, you can already see what's going to happen. There's no Vs that is shown up in here. There's no Vs here, right? There's just the alpha that's set in the momentum balance equation. So it couldn't have mattered. It had to disappear somewhere along the line, 0 or not. Okay. This was 1, 2, 3. Yes. It's not clear. Well, what it's telling you is you are not necessarily dissipative back down to the isotropic state. You have to do more than this. Yeah. Okay. So let me just, because I need this and it lets me make some other points to bang you on the head with. So as I said, this is this 3 + 2 theory. It's useful to get rid of some degrees of freedom. We just look at things in space. Generally, that's often all we have access to, maybe concentrations and things like that. So let's look at the evolution of moments, just a couple of them. And it suffers from the usual closure problems of any of these kind of kinetic theories. Moments of psi. So there are some important ones. There's the concentration of swimmers, which I'll call phi. So it's just the pointwise spherical average of psi. There's what's called the polarity, right? These things have a direction, so they have a polarity. They swim in a certain direction. Though their stresses are apolar, right? Because they look like PP transpose. So you change P, you don't change the sign of the stress. Phi inverse, DSP, psi, P. So this is the polarity. This is concentration, polarity, and then there's the Q tensor. Oh, I shouldn't put a hat on there. There's no reason why the polarity, in fact it's generally not, should be a unit vector. It's just an average of unit vectors. If everybody's swimming like that in opposite directions, you'll have a polarity of 0, even though there's lots of stuff going on, right? And Q, phi inverse, the second moment is just phi inverse times D, which is phi inverse DSP. I just wrote it down up here. It's D. I don't need to write it again. And this is often called the tensor order parameter, which shows up very commonly in describing rod-like systems that have liquid crystalline behavior, have orientational alignment effects and things like that. Landau-Dijen theory, or these types of theories where you include Meyer-Salpe interactions to bring in alignment effects, if that means anything to some of you. Okay. So let me just write down the first two, just to make 2 points. The evolution of phi and of n. So all you do is you integrate p against, or 1, against the Fokker-Planck equation and average that thing over the sphere and see what you get. So what I get, I want to put Vs back in just to keep track of things a little bit, see what depends on Vs. So let's reinsert a placeholder Vs. Okay. And then what I have is d phi dt, and that's the substantial derivative with respect to the background U field. Okay, not the part that includes the swimming advection, plus Vs div x dot n hat phi is d Laplacian phi. Okay. Now, let's just look at this a little bit. So I could rewrite this as del phi del t plus u plus Vsn. Someone spill something? You're not supposed to have drinks in here. Yeah. Yes. Dot grad phi. And then there's another term over here that comes from distributing this guy over here, and it's minus Vs phi div dot n plus d Laplacian phi. What? I'm sorry you're sorry, but it's this guy, it's the polarity. It's that guy right there. Oh, it shouldn't have the hat. I'm sorry. Yes, thank you. I have a really hard time writing down an N without a hat. It's just reflexive. I can't, yeah. You know, go back to your vector calculus days and normals on surfaces and all this kind of stuff. It's just is beaten into you. Okay, but what is this saying? This is an advection term that along particle paths does not change the value of the concentration, right? And what this tells you is that what changes the concentration here are divergences in this polarity field. Okay? So it's the divergence of the polarity that drives changes in concentration. So if you like, you could call that effectively the mean swimming velocity, something like that. It's not really that. So if Vs is gone, if there's only this activity, but there's no swimming, then you can see that you just advect concentration around without change. But if you have swimmers, they can create concentration fluctuations through this type of field. Okay? Okay. Now, let's write down the dynamics for n. If I look at d dt phi n hat, you can simplify this if you want, but it's vs div dot d plus, and this is an ugly term, but we'll simplify it in a moment, phi in, oh sorry, the hat again. See, it's just impossible. So this is a third rank tensor. This is delta ij nk. That's what I mean by that. That is not a multiplication. It becomes clear that it's not, once I write down this, the average over the distribution function of PPP. So obviously IN meant a third rank tensor because that's what PPP is. Contracted against grad U. So the ij part contracts against grad U. Or rather, I'm sorry, the jk part, because I have this guy on the right-hand side. Then I have plus d Laplacian phi n, no more hats, minus 2d phi n. So here's now rotational diffusion shows up. And it's interesting that under these kinds of averages, not so crazily, it shows up as just a simple dissipation term. Okay, not a scale-dependent kind of thing like the Laplacian. The main point I want to make about this is just an obvious one. And that is because each of these equations, I'm depending on higher order things in this kind of moment hierarchy, right? So the evolution of phi depended upon n. The evolution of n depended on a third moment and on a second moment. Okay, so these things never close. So that's called the moment closure problem, typically. And if you want to get cheaper theories, things that might be easier to analyze or things that are easier to simulate, then you have to think about how to do closures, how to express higher moments in terms of lower moments under something that's reasonable, something that's accurate, it preserves something, has a variational structure, something. But that's the moment closure problem. So I'm going to look at this in these moment equations in a case where I have no moment closure problem. So if you look at moment closure schemes for Doyon-Sauger rod theories, you will find a dozen different schemes to do this. So there's one that goes back to Hinch and Leal, which is basically an interpolation of being in isotropic, being in a very ordered state. There are other schemes that are called L closures and P closures. There's all these kind of weird closures. The one that I am in favor of, actually, which I personally like, is one that's called the Bingham closure. I have my favorite. And the Bingham closure is kind of a quasi-equilibrium closure. It says I'm near to being in a highly aligned state, and I'm going to use that to make some approximations. Yeah. It's an unsatisfying field, really. Okay. So number 4, I'm going to get rid of this now. We've looked at it long enough. So I want to use this to do a simple analysis of orientational instabilities. And I'm going to do it in a special case where I don't have any dissipation in the problem. I take all the diffusions out. Okay? Just because it's a nice case where you can do everything. Pardon? Yeah, I haven't written down. These are just expressions for the Fokker-Planck equation, right? Yeah. So the Fokker-Planck equation, you know you need at least an approximation for D. I mean for the momentum equation, right? Okay. And this is really the first instability in these kind of hydrodynamics of swimmers that was identified. And this first version goes back to Ramaswamy and Simha, as far as I am aware. And it's PRL. I think it's 2002. Though in my notes I have it both 02 and 04, and I haven't gotten the energy to go and look. But you can find that. And I'll give a slightly more elaborate version that identifies some other branches of instability for you using this theory. So here's the idea. So let's set my diffusions to 0. Okay, and what is now consistent with that is to assume that I have a suspension that is sharply aligned. Okay, if I have no thermal diffusion, if everybody's kind of lined up in the same direction, there's nothing to knock them out. And if I get rid of D, then there's other problems that disappear. Okay, namely it would get rid of a delta function that I want to use. So what that means is I'm going to look at phi, so this is an ansatz, where phi of x, p, and t has the following form. It's a concentration times a delta function in orientation. Now what did I use? I called it n, I suppose, because in this case n will be a unit vector. Yeah, that's fine. Okay, so I'm going to make that ansatz. So everything is perfectly aligned. My distribution function is a delta function in orientation times the concentration. Okay, then you can rewrite these moment equations, you can close them. Okay, because Q, or let's say D, just becomes phi n hat transpose, for example, under that assumption of a delta function in orientation. So everything will close. You can express all the higher order moments just in terms of n. It becomes very simple. So all you need is the evolution of the concentration and the evolution of n. And I'll have a closed system, and it looks like this. It says phi t plus divergence of u plus n hat times phi is 0. Okay? And I have nt plus u plus n dot grad n is equal to, I have just Jeffrey's equation, I minus nn grad u n. So here's a little exercise. Show mod n hat equal to 1 is preserved by this dynamics. Very simple little exercise. Jeffrey's part is clear. It's going to be the advective part yet to play with a little bit. Oh yes, there should be. Oh, it's right here. For D. Oh. Sorry, too many voices. Where are you again? Ask your question again. On this one right here? I mean like this one. This one. That's what survives of the rotational diffusion. It's dissipative, but it is not scale dependent in space because it's not something that acts in space, it acts in rotation. Do the calculation, show this is what it looks like. Yeah. Yeah. Yeah, sorry, it's just what it gives you. Yeah. It's kind of an unpleasant little calculation, unrolling a couple of grad t's. I really hate these things on the sphere, but you can do it all. Thank you, Julian. Then I have minus Laplacian u plus grad q is equal to alpha div x dot phi n hat and div dot u is equal to 0. So in this special case, I have a closed set of nonlinear PDEs. This is actually an interesting system to play with. In fact, lots of analysts like to play with these types of systems where you put in kind of subs for kind of various types of ways of cheating as though you had diffusion in them. So they will do more interesting things. Okay, but here's the thing that interests us, is that let's say that I start everybody off, I choose phi to be identically 1 over 4 pi, just the uniform concentration, and n hat equal to z hat, the z direction. That just means I have a uniform concentration of swimmers all swimming up. Okay? That's an exact solution to these equations. So this is an oriented, globally oriented set of swimmers. It produces no flow, no background flow. You have to be a little careful in your intuition here, because you say, oh, but they're dragging all this fluid up, right, as they're moving, or they're pumping all this fluid down. Both of those are kind of the wrong sides of the argument. They're both pushing fluid up and pushing fluid back, right? That's this dipolar flow. So in this mean flow, it doesn't see anything as a consequence. And that really comes from the fact that they're dipolar swimmers. So you can have no background flow, even though everybody's moving in the same direction. Okay. So now we can do stability. I love doing stability. In my group, we have group meetings. I talk about stability calculations, and people roll their eyes a little bit and say, oh, Mike found another stability problem. But we have to be polite. So that's the question. Stability. Okay? Yes, it does. Well, it's self-consistent. Yes, it is obvious if you work through the moment stuff. I mean, it's easy to break this, right? A little bit of thermal, any sort of diffusion will break this. Yeah, yeah, yes. Dragged, yes. Well, that was that construction of the microscopic model that we went through when you looked at once I chose that I have to think about if it would change in different types of models. My guess is it doesn't. But when we constructed the microscopic modeling, we assumed that the propulsive stress was uniform. This is another thing you could check just for fun, right? Once we assumed the propulsive stress was uniform, then we got that in the lab frame, those two velocities were equal and opposite in the opposite directions. It was just a calculation. There might be something more to it. It would be interesting to check that in a case where they're not the same, but you still have zero force bounce. That's a good calculation to do. Right, but the point is that that flow has zero mass flux associated with it. So kind of the background flow that it produces in kind of ensemble, you don't see. It's zero in this mean field. Well, that's also true. Yeah, no, that's also true. Yeah. Yeah, now I have to think about that argument. That's a better one. I like that. I constructed this one this morning while I was sitting in my room. That's true. So you can get, of course, now it's a bare stress gradient. Yeah, so it has really to do with uniformity. I guess that's the better way to say it. Yeah. Thank you. That's a better answer than the one I was giving. Uniformity of stress. Uniform stresses never produce anything, and we produced a case of uniform stress. Good. I should let you guys have access to my LaTeX, and you could go in and put in these comments. Okay. So one very important point of speaking to the public is you always have a reason for everything. Like mine are usually correct, but once in a while they're a little bit off. But say it with authority. Okay. So we can look at the following. We can say, okay, I'm going to look at phi is 1 over 4 pi, 1 plus epsilon phi tilde, right? Epsilon much less than 1. And then I could have that n is z hat plus epsilon eta, like that, epsilon much less than 1. You're going to have a constraint because mod n has to be 1. It's related to something that has mod 1. There's a constraint that there has to be orthogonality in linear theory between eta and z hat. So this is going to require z hat dot eta hat. Eta is 0, just to keep mod n hat equal to 1, the second order. Yeah. Well, I just showed you a calculation that said if I have divergences in n, density will not be conserved. Yeah. But that's an interesting point that's going to come up again. No, that was a local statement, actually.
Yes, but what I mean is you're saying that the uniform field is gained, like the uniform density is changing in some way.
No, I'm not. What I'm saying is that my steady state has a uniform density. Now I'm allowing that to be perturbed. Okay? So, okay. So you take this, you stick it into the equations, you expand the first order. You look at the first order system. And now I'm not going to go through the calculation because you can find it in papers, but I'm going to say what the main point is. Okay? I have it carefully written down here. Okay, this is the main point. This leads, so let me say, more particularly, when you write down these, let me get rid of this. I'll just write down this way, 1 over 4 pi plus. Okay, my phi tilde. I don't like calling something phi tilde when it's going to be multiplied by the steady state, so I'll leave it like that. Just a question of taste. So when you linearize everything, you're going to realize that this allows for plane wave solutions. Okay, so this phi tilde is really going to look like a e to the I k dot x. And eta is going to be b e to the I k dot x. So it allows plane wave solutions. And so once you do this, then this leads to a complex valued quadratic eigenvalue problem. And it's going to be parameterized by the angle phi between E hat of phi, written, it's on the unit sphere, so this is sine phi cosine theta sine phi, sine theta, cosine phi. So here, this is the azimuthal angle. K is fixed. When I'm saying that it's a plane wave solution, I'm picking a wave vector. And then I'm going to sum over all wave vectors to write down a general solution. But everything diagonalizes wave vector by wave vector. That's what it means to have a plane wave solution. Okay, so I have a K here. Maybe I'm not even answering your question.
The point is whether we should still call phi the polar angle if it's 90 phi.
That is excellent. So yes, phi is the polar angle. Yeah, I turned around and I made you a little lecture, and then you slid the knife in after I was done. That was good. Okay. So here's the z hat direction. That's the direction of swimming. And then I have a plane wave vector that I'm looking along of phi. Well, phi and theta, but let's just say phi. Theta does not matter in this, right? Why should it? I just wrap this thing around in theta. It should all look the same as far as growth rates. What matters is the orientation of the wave vector relative to the direction of motion. That's the only thing that can matter, right? So I have this angle phi. And so what you find is that for every phi, there's a solution to the quadratic eigenvalue problem that has positive real part and negative real part. Can't have both. There's a solution with positive real part and a solution with negative real part. So for any plane wave vector, you always have an unstable growth rate. Okay? So then what you find is for any phi, there is a solution to the eigenvalue problem. There is a eigenvalue, or growth rate. I don't want to call it a growth rate until it's positive. There is an eigenvalue with positive real part and another of negative real part. So you have instability. Oh, I should write this K. I should put a, right, so K phi. Jesus, why am I appealing to Jesus? I don't know. But I have this K of theta phi, which is mod K times a unit vector. That's what I'm trying to say. So I have two things that come in here. Actually, I said it a little bit incorrectly. So it's parameterized by the angle phi and the wave vector, modulus of the wave vector, the frequency. And then here, you're going to be looking for solutions that, once you write everything out, that look like, a tilde e to the sigma t, b is b tilde, e to the sigma t. You get a quadratic equation with complex coefficients for sigma, for this guy. And that's what I'm talking about. Okay? So you have two sigmas that come out for each mod k, each phi. One has negative real part, one has positive real part. So it's always unstable no matter what the perturbation is, no matter what the wave vector, the wave number is, or the polar angle. Okay? Now obviously if we start putting some other things back in, for example, if we put in spatial diffusion, then we're going to start controlling the high wave numbers in this, things like that. But this is kind of illustrating a point. Oh, geez. It's too messy right now. Yeah. It's too messy at this moment. Okay, but I have to say you should construct this eigenvalue problem, this quadratic eigenvalue problem. Just write down the solution, sigma equals minus b plus minus blah blah. And there's just a nice little place where you can point where you basically have something that looks like a unit circle with a perturbation So you have some eigenvalue sitting outside of the unit circle, and then that means another one has to sit inside. You know, there's this kind of cute little geometric construction you can do to prove this thing. Okay. It's just an eigen, you know, it's just a wave vector. Yeah, so, yeah, yes. Because remember, I don't have any diffusion to control anything, right? Of course. Yeah. I'm really thinking of this as being like a long wave phenomena. But I can do it exactly in the case here. Now, it turns out that if you include ordering interactions, then you can write down more general solutions to this problem where you don't have to throw, because when you include ordering, you're balancing kind of collisional torques against thermal fluctuations. You get to keep that, and you get to keep the translational diffusion. So you can do it more generally, but it turns into a numerics problem rather than something that's by hand. But you needed to included some other things, other types of solutions that are more general. Okay. Because I decided to. Yeah, that's it. You said it correctly, because I decided to. Because I like a calculation where I can do it by hand. If you include diffusion, you cannot do it by hand. Because you don't have the ansatz. When I have the ansatz, I end up with these closed PDEs, and I get to analyze them. I like that. It's fine if you don't like it. I'm okay. Yeah. Okay. Now, let me say a little bit about the form of this solution. So what I want to plot is the real part of sigma, and I'll have two branches, versus phi. Okay? And the first one I want to draw is the case k equal to 0. So you take the limit mod k goes to 0. So the long wave problem. And this is the problem that was looked at by Simha and Ramaswamy. They constructed that solution. So this long wavelength limit. And it looks like this. So let's take this up to pi. That's not a bad rendition. Okay, so they found this branch. There's another branch which is just 0. So there's two branches. One is just 0. It's kind of a degenerate case. It's, you know, instead of having a positive or negative real part, it just has 0. So this is second branch. And the point with this is that they did find these negative growth rate, these damped directions, okay? And the other thing is that the maximum growth rate in this problem at k equal to 0, and this is preserved as you change k, is that it's the direction, it's the wave vector in the direction of the alignment. That's phi equal to 0, phi equal to pi. Phi equals 0 is the direction of maximal growth. So that's already consistent with those simulations that I showed you, and consistent with some experiments that I showed you. Oh, it works for pullers or pushers. This works for either one. The eigenvalue problem changes a bit, but the basic conclusions are the same. Oh, is that right? Do I misremember that? Okay, so this is a pusher plot, I think, then. I don't think so. This is pusher. This should be pusher. Okay, yeah. Let's look at it again because I had forgotten this. I had forgotten this point. Is that okay? Okay. So we're hoping that's pusher. So then the other claim is if it's pusher, I flip this thing down. But the I guess what I meant was the part that gets preserved is you always have a growth rate. One's negative and one is positive. Yeah. I haven't looked at this really in a while, so I'm glad someone is on top of the details. Okay. Now, but the thing is as soon as k is not 0, then this 0 growth rate is no longer 0. Okay? It pops up, and that is this result. And so if you took a look at some k that was bigger than 0, it might look something like this. Okay? And then there would be another part that looked like that. Okay? Okay, but this is the branch discovered by Simha and Ramaswamy. Okay, so that's the orientational instability, and you can look at the details. Sounds like there's a couple of people to ask in the audience on that. And now, what I want to talk about, but the main thing, at least for pushers, I guess, I had to be corrected on that, is that the mode of maximal growth is the direction in which you are aligned with the suspension. There's another instability. And it's the instability of isotropic suspensions. Yeah, let's look at this as soon as my talk's done. We'll straighten it out. Okay. So we have another solution, of course, and here it's actually easiest if you set the d's to 0 and all that kind of stuff again. Becomes almost an analytical calculation. There's an integral equation that you have to solve numerically, but you can do it. And so what you're doing then is you're linearizing around 4 pi, say some phi tilde. Okay? And in the case when these guys are 0 again, then you can calculate almost analytically a stability threshold, a stability criterion. Oh, this guy, by the way, gives rise to another eigenvalue problem. But because we don't get to average out the p degrees of freedom, and there's this integral that involves the stress over p and these kinds of things, it's not a constant coefficient problem. You can formally write it down as an eigenvalue problem if you think that's okay and find solutions, but generally you have no reason to think you can solve it as an eigenvalue problem. Some more generalized linear stability thing. So, but I'll just show you what happens when you make the ansatz that it's an eigenvalue problem. So what you find, and here I'll just write it in terms of mod k here, is that you have a real part of an eigenvalue that looks like this. So this is real sigma. This is imaginary sigma. So let's call this thing K1. So at K1, there's a split from 0. Then you go up to K2. And then it turns out that for the dispersion relation or growth rate relation that you get, you can show that when these guys are 0, you have no solutions of eigenvalue form beyond here. it stops. You can do a local analysis and show that if this k is above k2, there's no solution to your eigenvalue problem. Okay, so it stops there. Turns out if you add a little bit of rotational diffusion, it does something like this, and it gives you existence of this branch again. But this is for d equal to 0, little d equal to 0, and this is for d positive. Okay. But interpreted as though, you know, up here you go into stability, then this would mean that I have a long wave instability in the problem. If I start off with a box that was sufficiently small, then the fundamental mode of the box would sit up here somewhere above this crossing point. As you make the box bigger, then you will cross and you'll allow yourself an instability as you cross this point with your fundamental mode. So fundamental mode means k equals 1 in your scaled box, right? So this would be the sign of a long wave instability. If I imagined it kind of was really stable down below that. It turns out that it's neutrally stable. There's some analysis that we did in a paper in 2010. You have to look at it differently as kind of a Laplace transform problem. Okay, so what this guy turns into, though, when you put yourself back in terms of expressing what it means to have this critical wave number in the problem. If your system gets big enough, then you allow that wave number into your box. What that means is the following, and it's a very nice statement. And again, this is pushers. Pullers, this whole diagram for d equal to 0 gets flipped down and everything has negative growth rate. Okay, so that's for pushers. There's no instability in this theory for pullers. And this is saying I have something that I'll call an activity parameter, which looks like mod alpha because alpha is negative. Okay. Times this effective volume fraction. So this nu look like the number of swimmers times little l cubed over the system volume. That's how that was defined. There might be a 2 floating around in there. Times L over little l has to be bigger than some critical A star. Okay? For instability. So the way to read this is that either you're going to have an alpha that's big enough so you have enough activity, or you're going to have enough swimmers in concentration, in this effective volume concentration, or your system size is going to be big enough relative to the swimmer size. Any of those effects will drive you across some critical activity number that you can calculate, and you'll become unstable. There's another way you can write this. You can reform this parameter back in terms of the original stresslet definition and all these kinds of things. It has kind of a nice form. So there's some coefficients that I'm not going to worry about, so I'll call that A tilde is, write it this way, it's the number of swimmers times the stress that you estimate that they give you in this volume. So this is the total active stress. Remember that the stresslet look like a force times a length. So sigma over L cubed looks like a stress. Divided by, U over L, an estimate of the viscous stress. Okay? So it's saying when this is bigger than some critical value, when your swim stress is big enough relative to the viscous stress, then you'll become unstable. So it's just kind of nice form. Okay, so when you start putting in numbers, and what we get to compare with is with our simulations, it's kind of roughly within a factor of 4, consistent with various experiments of Igor Aronson actually earlier. But with respect to our swimming suspension stuff, we get within a factor of 2 of concentration, where all these thresholds happen and things go unstable. So it's kind of effective. Now, I think I have chewed up we say in the States, a shitload of time. And I'm not going to get to cellular stuff at all. I will finish more or less where I wanted to finish the first 4 lectures. But, yeah. Well, these would presumably be, yes. You know, it's a funny thing is that you should get waves. We haven't really concentrated on that, but we don't really see waves. But there should be linear waves. I would say we haven't looked hard for them. We're probably working more on this very unstable part. Good question. There's no reason to believe you would not get waves. Yeah. Okay. Now, oh, doesn't have telepathy. Just to show you some stuff. Okay. So this is a simulation, a 3D simulation on the right, showing from isotropy, the onset of kind of mixing flows in this type of system, in this kinetic theory. And that should be plain. And what it's showing you is density, actually. So you can see we're starting off at a case where it's just a perturbation from being... Speak to me. Let's try this. There we go. See if I can turn this guy off. Yeah. Okay, there it goes. So this is showing the oh, there's another point I forgot to make, so I'll just have to say it. So this is the growth of density fluctuations from a nearly isotropic state. So you can see you get these swimmers as represented by this mean field forming density fluctuations that are going around, and the nature of density fluctuations is interesting. So, but you get this very kind of chaotic time-dependent code flow. And one thing that comes out of this model, you'll notice, is the highest growth rate, at least for pushers, I'll say, is always happening as k goes to 0, at the longest scale in the box, okay, or in the system. So, so kind of what sets a scale is an interesting question. That's kind of still debated in various ways. And this is the kind of mixing that you get out of these types of flows. So this is a 2D unstable flow just pushing around, kind of intrinsically generated in a pusher suspension, pushing around a dye field. So at least by eye, they're good mixers. You know, when you write grants, I'm sorry for those of you who are going to have to start writing grants at some point. It's a very unpleasant business, and you have to say things you don't really believe. And part of every grant has to do with the wonderful applications that are going to come out of active matter. And it's a little, hopefully that all happens and the field becomes even healthier and these kinds of things. But we are still waiting, I would claim, put forward, to start seeing outside of kind of understanding biological phenomena, more in kind of the engineering and device realm, we're still waiting for like a killer app, right, in these kinds of things. But the standard thing that you say is, oh, we're going to figure out how to mix stuff. We're going to figure out how to transport something to a tumor with a magnetically, guided thing. Some of those things you start to see glimmers of them happening, but we're not there yet, but we're going to have to be, I think. Is that okay, Julian? Yeah. So, so as I said, a lot of this doesn't depend actually on having self-propulsion. It depends on having unstable, these kinds of dipolar stresses. And there's various types of systems that you expect to see these kinds of things in. So there are various types of bacteria that when they divide, they will just keep connected, kind of end to end, and they keep these kind of long growing strands. That's associated with something like a dipolar flow. You can manufacture little active particles that flux fluid from the middle to the end to create kind of mobile but non-motile devices. I shouldn't call it a device. They like to call them nanorobots. I'm not quite sure what they're doing. But, or in these various types of microtubule assemblies where you have things like kinesin that are conducting polarity sorting of things, you expect to get extensile flows. So you can play with these types of theories just in the case of, you can find just some kind of fun things to do just in the case of having no motility, but just this kind of destabilizing active stress. And so, for example, so this is simulations using a moment closure scheme, the Bingham closure I referred to before, for basically this kinetic theory, but with no Vs. Vs is set to 0. And so, and this is also including something that gives you a liquid crystalline-like response, so it becomes an active pneumatic model in that case, in kind of the Landau-Dijen style, though it looks different. So, you can, and some of this really goes back to Woodhouse and Goldstein, who did some of the first simulations showing that you could get auto-rotation of active flows just from their internal activity. But when you have low activity, then, for example, you can start off with a material. It wants to align because it's liquid crystalline now, so you'll relax into a aligned state inside of a container. You start turning up the activity, and then on top of that state can become unstable to an alignment instability. And this is something where you have something like an alignment instability that leads to kind of defect motion moving around inside of this container. So there's a couple of disclination defects moving around. You can have cases where they run into boundaries and disappear. Sometimes they can, you hope, appear from boundaries, things like that. And this is showing the vortical flow that comes out of it. So you can make little mathematical models or computational models of what I would call, like a propulsor and a rotor. And so this is my now ex-postdoc Tony Gao. This is using the same type of model where you make a bubble of material and you let it go in a fluid. And because of defect dynamics inside of this guy, you can make little objects that propel themselves around, which is kind of cool. Or you can make little washing machines and throw your micro socks in there. Okay. Things like that. So I don't think I'm going to talk about this. That's older work. Here's more or less what I was going to tell you about a little bit. How much time do I have left? I'll just introduce you to another area. And I have 10 minutes, I think, right? A bit more, okay. Oh, 20. I'm going to switch talks entirely then. Didn't know I had 20 minutes. Okay. So I was going to give you a kind of an hour-long talk on some of the mechanics problems that we're working on inside of the cell. And a lot of this is how you move nuclear material around so that it does what it needs to do later so the cell can divide. And that's work mostly going on with Dan Needleman's group at Harvard. And I don't have Dojic on here, but we've been doing some materials modeling too about when you pull material out of the cell, microtubules, and you have kind of nice extract systems or in vivo systems where you just have a few elements and you have microtubules and motors and that kind of stuff in a very stripped down way, and you look at how they behave so you can build more complicated models for what goes on inside the cell. Okay, so I think probably a good many of us have seen these very famous drawings by Ramon Cajal, who would draw the processes of neurons, right? Really beautiful drawings. And it turned out he did a little bit of work on drawing mitosis, which is the process that goes on as you go into the first cell division. And so here is what's called a spindle, mitotic spindle. It's not shown here, but there are, not seen here, but there are chromosomes in pairs that are sitting in here, and the spindle is going to pull those pairs of chromosomes apart, or maybe I'm already infecting you with a certain point of view by saying pulling the chromosomes apart. It's not clear that's what's actually happening in every organism. Maybe they're being pushed apart. And you end up with copies on opposite sides, and you have a cell division, and life goes on, right? So this is what a mitotic spindle looks like in a model organism that is studied by hundreds of labs. And this is a C. elegans embryo. There's a cell around here, a cell wall. But what you're seeing is, in what's called metaphase, what you're seeing is a spindle, which is kind of this structure right here, which is made out of microtubules. You see chromosomes have condensed into a plane out of the innards of nuclei, have condensed onto a plane here. In a little bit, these guys are going to separate into two pairs and go off to their other sides. And at the ends of the spindle, you have what are called centrosomes, and centrosomes are microtubule organizing sites, nucleation sites. And this whole dynamics, which I'm just showing you a snapshot of, is really orchestrated by things acting on microtubules. Microtubules are kind of the force carriers in one way or another from other forces being created, for example, maybe by polymerization, their polymerization against walls, or from motors pulling things along them or pulling on them. Okay, now this is actually an electron tomography micrograph. So this is, they have taken a cell, they have frozen it suddenly, they have invaded it with plastic and displaced the water, and they've started to slice it up, image it with an electron beam, and they reconstruct it from that, and they reconstruct this three-dimensional thing. So there's about 20,000 microtubules in that object right there, and it's complicated. So since it's complicated, I'll give you a fly-through. So this is from a lab in Dresden, Thomas Müller-Reichert, working with his student Steffi Redemann, and we are part of a collaboration with them to construct mechanical models for how some microtubules behave in all of this mess. Okay, I love this, So if anyone ever shows you a numerical simulation with a fly-through, that means they have no digits of accuracy. If they show you a number, that's something. A fly-through is at the other end of the spectrum. So accuracy is ordered by single number, graph, surface, fly-through. Okay. Anyway, so there it is, very complicated, and something about the cytoskeleton. But let me just show you a little movie, and this is from a lab in Tokyo at Tohoku University, run by Professor Sugimoto, who has let me use some of her data. And so what you're seeing here is the dynamics actually associated with the mitotic spindle that I showed you at some frozen time. So you're kind of caught between a rock and a hard place here, because you have this beautiful data which is very coarse scale from microscopy, And then you have incredibly detailed data at a single point in time from things like tomography. And so it's kind of an interesting place to be as a modeler, trying to straddle these two things. Okay, but what you're seeing here is the male and female pronucleus, so that you have these two nuclei that are in the cell initially. And what has to happen is that these guys need to be moved into the center of the cell. It needs to rotate into what's called proper position, so that these nucleating sites are lined up along the long axis. Then you get chromosomes condensing, the formation of the mitotic spindle, chromosome segregation, then you'll have a cleavage, membrane cleavage, and you'll have a cell division. That's the rough dynamics of the first cell division. And there's kind of a movie of parts of this. So what I was going to tell you about was first modeling for how you actually get this thing into the center of the cell into proper position. And then I was going to tell you about various dynamics that's associated with these later stages. For example, what you will see here, watch this. Keep track of those two guys right there. And now it starts to oscillate. Okay? So at least in C. elegans, there's this very characteristic oscillation of the mitotic spindle as it enters into what's called anaphase. It's this phase where it's assumed proper position, the spindle starts to stretch because the chromosomes are segregating, and then it starts to oscillate simultaneously. It turns out that that oscillation has been much studied by many different models, and the reason is it's so clear that there's some sort of weird force balance thing going on there that's giving you some sort of bifurcation, probably a Hopf bifurcation, right? It turns out that oscillation is not important to the things that the cell needs to do, but it's a nice signal for understanding what the forces are that might be acting in order to have all this happen. So there are 3 models, roughly, of how forces are transduced onto microtubules, which are then transduced onto things that they're attached to. So one is, this is a very interesting aspect. So I showed you this movie just now of this thing moving into the center of the cell. That's probably somewhere on the order of 10 minutes, I think, in real time. The microtubules that, if you don't have them, none of this happens. The microtubules that are making this happen live very briefly. They have lifetimes of around 20 to 30 seconds. So you're forming all of these processes, which you can track clearly in microscopy. You know, it's kind of these coarse-grained objects on the orders of minutes or tens of minutes. But the things that make it up live only for a little while. And so they're constantly, these objects, microtubules, are constantly depolymerizing and then regrowing, depolymerizing and regrowing all the time. But the fact that they regrow means if a microtubule runs into a wall, it's just a linear polymer, and it grows by end growth, right? Putting more dimers here on the end, it can exert polymerization forces, or it can exert forces from its polymerization on a wall and push things around that way. Turns out that the walls of the cell also are known to have motors that will grab onto microtubules and pull on them, dyneins. So there are motors that do that. It's also known that dyneins can coat organelles inside of the cell, and they can attach onto microtubules and drag those payloads around on the microtubules, and in that way exert forces. Right? If I'm a free microtubule and I have a motor attached to a big ball and I start walking along that, I will push the microtubule in the other direction to which I'm walking. So now imagine that microtubule is attached to another payload. So I was going to tell you about that. 5 minutes? Yeah, excellent. So there's a lot of things that I said about polymerization, small lifetime, actions of different types of motors. I think you've heard earlier about all of these microtubule motor polarity sorting suspensions. Those typically involve another kind of motor called kinesin. In this type of modeling, you're really worried about something else called a dynein. And here's an early simulation that we did about 7-8 years ago of this kind of centering process where it's the model where I have payloads being carried along microtubules and in that way exerting forces. Okay, so this is a 3D fluid mechanics simulation. And what it's showing is a bunch of rigid microtubules attached to a payload. Motors are attaching to them in the bulk and carrying payloads along them, so they're kind of pulling on it. And if you have longer microtubules in one direction, you tend to get pulled in that direction. There's a force imbalance. Stasis is when you reach the center, and it turns out that being lined up with the long axis is a stable orientation for this kind of mechanical system. The problem with this simulation, and this is why I talk about slender body theory, though I didn't talk about it in its non-local variant, is that this is an immersed boundary method. That will not mean anything to many of you, but it's a volume-based method. It's not an integral equation-based method. And what it means is you can't resolve things as well as you might like because you have a volume grid. So we were only able to do 25-ish microtubules. Yes? They're implicit. Yes, thank you. So there aren't explicit payloads being moved along these microtubules, but it does properly satisfy Newton's third law. And so in the sense that as a microtubule extends into the cytoplasm, we have a continuum of motors, if you like, that pull on it. So you'll have a pulling force that's proportional to the length of the microtubule, and you have an equal and opposite force that you exert onto the fluid. Because you imagine if I'm a motor and I'm carrying a payload, I'm pulling on the microtubule upon which I'm walking, but I'm dragging this payload through the fluid. So it's really a force dipole again. You have to have an equal and opposite force on the fluid as you do as pulling on the microtubule. So this preserves that. That really goes back to a model originated by Kimura, a Japanese biologist. But we couldn't afford to have many things that are real about microtubules, and here's one of them. This is just a little bit of low Reynolds number scaling. I think I mentioned this already to somebody in the audience. Let's say I have a 10 micron payload, 10 microns in diameter. I have to drag through a fluid. And let's say, and I have a certain velocity I go at, so that requires a certain force, right? There'll be a drag force associated with moving at that velocity. Now let's say I look at a microtubule that has the same length as the diameter of that object, but microtubules are 25 nanometers in diameter in their small direction. So these are long but tiny little things, right? What percentage, it has a drag if you move it at a velocity. What percentage of the total sphere drag do you think it has? Maybe it's 1%, right? Turns out it's 25%. This little thing, which is 25 nanometers across, nonetheless has a drag which is 25% of something which is orders of magnitude bigger in terms of its area that you're pushing through. And that's because drag in the Stokes world doesn't depend on an area like it does at high Reynolds number when you're pushing a race car. It depends on a length. It depends on one bare length. So it's a weird world where long, skinny things have almost the same drag as the objects they might be involved in moving. And in these simulations with immersed boundary, we couldn't afford to resolve the drag that was associated with the microtubules. All we used it for was a direction of force onto the motor and a place of exerting forces on fluids. So that's why we did all, so then there's this whole story about non-local slender body theory as a numerical tool to talk about the dynamics of microtubules in a way that handles all the hydrodynamics for long, skinny things. Now, I'll leave that aside, but that's how we did all of these simulations. I showed you one of them, of these different models of things being moved around inside of cells. So these are 3D simulations inside of a cell of order of 1,000 microtubules interacting with motors and boundaries and pushing against things by polymerization forces. Seeing if we could see big differences using reasonable physiological parameters between the three of them, what they could or could not do in relation to what you see in experiments. And what we discovered is that all of these mechanisms did exactly the same thing. They got something into the center of the cell, there was a torque instability that let it rotate, and you ended up in proper position, which is a terrible, terrible position to be in. But the one way in which they were different is they predicted different flow types in the cell because they corresponded to either having something like a force-free object being moved or something that was under a mean force because it was being pushed or pulled from a boundary. So they predicted different types of flows. Okay. So, well, I should say, I put this in here because I wanted to. So we built these numerical methods, and one thing that Wen sitting here has been very much involved in is advancing our whole technology with slender body theory to include things like collisions and all sorts of stuff, as he talked about out there. Okay. So in comes Dan Needleman. So Dan became convinced that maybe there was something to look at in this case, and he had this great tool, and this tool is laser ablation. So if you are exerting forces through microtubules, and you can cut microtubules, then you can look at how force balances are changed by the way in which the object that's being moved then moves. Pushing would be very different from pulling. If I'm pulling something, say, if something's in some position, some static position because it's being pulled on either side, and I cut one side, right, then it goes up. If it's in static position because it's being pushed and I cut, then it goes down. Very clear differences. So if you can cut microtubules, you can say a lot of things, not about magnitudes of forces necessarily, but the directions of forces. And that's what Dan did. With his student Hyen, they had this great laser ablation system where they can cut very complicated surfaces in the cell and ablate the microtubules there in that plane. Then they'll depolymerize and then grow back. And this is what happens, for example, when you ablate during this oscillatory phase in anaphase. And you stop me when I've got to stop. 2 minutes, okay? See, this guy's rocking. Goes up, you cut, and it turns out it accelerates down. And so you can do these types of studies, and what these seem to indicate all the way from this migration stage to what's called metaphase, where you're static there for a little bit, to anaphase, that really it seems to be dominated by pulling forces from the boundary. And there's lots of different things we've done on that. Well, yeah, that's an interesting question because you can choose where you cut. You can cut very close to the surface. So for example, when it's in migration and you cut near the anterior cortex, it's kind of a cup. It turns out that what that does is just stops dead. Yeah, which I found personally upsetting. Yeah, so. But there it is. And they were also able to do PIV by injecting nanodiamonds into the gonads of parent worms and having them be taken up by the embryos, and then they could do PIV and see what the flows were that were associated with that. And what we discovered is that the flows, so this is a long joint theory experiment paper we're putting together, is that the flows were consistent with having things being pulled from the boundary. And so when you're in oscillation, you set up these big flows where you're just dragging fluid around, and it looks very similar to the PIV reconstructions. We built a model. So first it's stochastic model. That's very stochastic. Sometimes it runs and sometimes it doesn't. There it goes. A simple stochastic model which just has drag and just a bulk drag and doesn't have fluid mechanics really in it. But kind of messing around with it, you can get it to do the right kind of things in all sorts of ways. We have built a coarse grain model which turns itself into some ODEs to analyze and shown that there's a Hopf bifurcation in our model that gives rise in this kind of coarse grain model to oscillation. And we showed that a lot of the stuff that was associated with what are called GPR12 knockdowns that have been done by Howard's lab and also by Dan's lab seem to be associated with the fact that when you knock down dyneins on the cortex, you reduce the amount of competition of motors for microtubules that are trying to hit the boundary, and that explains a lot of what goes on. So 2 minutes, yeah. So there's the migration part. So she cuts over here. Here's wild type. It just is going in this direction. But then if you cut as it approaches, then it just stops. And you cut near the cortex. Then I'll show one movie. Because another active process in the cell, I showed you this already, is chromatin. And it turns out that chromatin, if you do PIV on chromatin inside the cell, shows displacements in its position that are on the scale of microns and on the scale of seconds. And they all disappear if you knock down ATP. So it seems to be associated with motor activity inside of the cell. And we have a model that reproduces qualitatively some of these things. Are what? You don't. No, that's the model. Yeah. I don't, it's very complicated inside the chromatin. There's lots of processes going on. There's remodeling, there's enzymes doing things, topoisomerases, cutting stuff. So there's all sorts of things going on. But there seems to be some sort of self-organized activity that is creating large-scale displacements that are much larger than the size of kind of the individual. Right, so what we do is we say, oh, let's make life simple. And we're just going to say I have a chain and it organizes the direction of a dipolar force. So it could be maybe some sort of molecular object which is kind of pulling things apart or pushing things together. What's it do? So what we find is that when that activity is extensile, it reproduces qualitatively the kind of displacement correlations that you see in experiment. When it's contractile, it doesn't. That's the long and short answer. You don't know it's extensile, contractile. You don't know what it is, but you know that if you choose it to be extensile, you can reconstruct some of the data. And we're lacking a microscopic model for what that may be, and I think that's a very interesting question. Anyway, so there it is. And I'll stop there because I'm over time. And thank you very much. Let me say one more thing, is that I want to talk with several of you before I leave. I'll be around this afternoon, going paragliding tomorrow. I'll be around all day Friday. So I hope we can organize all that. Okay, thank you.